Hello everyone, thank you again for joining Mauser and onsemi for this webinar, Design Optimized Power Solutions for LEVs or light electric vehicles and enable efficient wireless connectivity. Those who join these webinars will know my name is Mark Patrick, Director of Technical Content for Mauser Electronics in EMEA, and joining me today is Alessandro Maggioni from the Advanced Solutions Group at onsemi. For those who might not know Mauser, we're a global distributor of the newest semiconductors, passives and connectors from over 1,100 manufacturers. We typically stock around 15,000 products from onsemi. If you're inspired by today's webinar and want to investigate their LEV solutions further, then we're likely to have whatever components you need in stock. Just a couple of housekeeping items to mention. Please ask any questions you may have on the presentation using the Q&A button below. It's just to the left of center of the screen, and we will answer as many as we can, either during or if it's appropriate, or at the end of the presentation. If you have any technical questions around audio or webinar function, then please use the chat function for that, and someone from the Mauser team will help you just as soon as we can. So with that, let me hand over to Alessandro to get started.
So thanks, Mark. So hello, everyone. So I'm very glad to be here today and having the chance to present you this exciting topic. Also on behalf of my colleague, Paul Klosner, that unfortunately cannot be here today since today is sick. So topic is light e-mobility solution for not automotive electrical vehicle. So let's have a chance. So let's discover the agenda of today's presentation. So we will start with an introduction to light e-mobility. So we're talking about its market and kind of application. Then we are going to break out into the main subsystem analysis, the related solution proposal for example, powertrain, battery chargers, human-machine interfaces and communication, battery management and its ecosystem, operational amplifiers for motor control, medium voltage MOSFET portfolio, and so on. So we will end with some key takeaways and then a session, of course, on questions and answers. So we hope we will enjoy this presentation and hope the final information will be useful for your project. So let's go and have a see into this topic. So light vehicles, market and application, starting with a market and application for light e-mobility. So here there are multiple reasons and motivation that push, let's say, the interest and the market behind this steep evolution of light e-mobility. So, for example, we have sustainability. Which goes together with environment conservation and protection, lower CO2 emissions, fossil fuel deployment, and also it's important to take into consideration health matters. We are all of us start to live in a more and more, let's say, crowded cities. So one of the key points is also to avoid road congestions. This means that also have higher efficiency and alternative transport choice. This slide introduces more numerical data about the light e-mobility market and let's say with a special focus on e-bikes. E-bikes market is very fragmented, so high competitive market. Today, we don't see a major monopolies. So, however, we saw that there are a few major players on OEMs, AMs side. From what regarding values, so the e-bike market was valued around $15.5 billion in 2019 and close to 24 billion in 2020. So this means that considering this growth and the statistic, we can expect a growing CAGR in the range from 7 to 12% until 2026. And we're expecting to reach up to 47.6 or 0.7 billion by that date, so by end 2023. So it's a really fast growing market. Which are the regions which are most successful and more growing? Let's say the faster region is Asia Pac. Europe is the second one. So today we have 20%, or we're expecting 20% of the total market. The major countries here, we're talking about Germany, Netherlands, Italy, and France. One other point to take into consideration that most of the e-bikes in Asia are different from what we were selling in Europe, so are equipped with lead-acid batteries and not lithium-ion. We saw a huge growing after COVID pandemics. So we see that most of the players, manufacturing tires, they were able to double or triple the sales compared to 2019. So it's really fast in growth. We say that about in Europe, 20% of share, Germany especially, market is what is called e-bike sales. So what's called a pedelec. So volume we can split in this way. In 2019, we had around 40 to 50 million units worldwide. Europe was in the range of 30 million units, and Germany only was 1.4 million units that way. And here you can see the links in which we have all extrapolated all these characteristics. Now, another related market topic here are the electrical motor and especially brushless DC types. So here we will see for several reports that the number are constantly and rapidly growing. So we see that the global market is for BLDC, so is targeted to be in the range of 17 billion in 2020. We're expecting to be 26.3 billion by 2028 with an average CAGR of 5.7%. So is divided by power segment. So let's say the main activities will be from 0.700 watt, from 700 to 3 kilowatt, 3 kilowatt to 75 kilowatt and above. How we can see here is basically that we can say that 70% of the global BLDC market share is included between 0 and 3 kilowatt. If now we are going to split a little bit more, which are the application in which this power range of BLDC motor are used, we can see that is quite wide. So we can go from fan, pumps, compressor, CNC machine, domestic appliances, mainly what we have every day in our houses, like refrigerator, freezers, air conditioning, vacuum cleaner, and so on. Garden and power tools becomes more and more common. Automotive, we are not only have to take into account the traction, but also all of the auxiliary motor controls. So we have like windows, trunks, all the kind of actuators inside a car. Medical, factory 4.0 drones, so on, and e-bikes and light mobility is exactly the category in which this power range is taken care. Here we try to map a little bit, so electrical vehicles and battery requirement. So we can see that all electrical vehicles have a common, let's say, physical requirements. So the fact that they have a battery, it's clear, which stores the energy and that allow the vehicle to be propelled. Let's say that in a similar way as a fuel tank does for an internal combustion engine, for example. However, the amount of energy required and the voltage involved can vary significantly. Depends on the type of vehicle and the power of the speed involved into application. We can say that here you can see in the graph. So you can go from a low voltage battery, let's say up to 60 volt for really e-bikes or e-scooters, go to 400 volt or higher power for e-bikes, motorbikes. Let's say we are talking about, if we're talking about e-cars, we are in the range of from 400 to 800 volt, which power in the region of 50 kilowatt per hour. And then, of course, we are going for heavy trucks. So what we're talking about, like e-mobility, are those kind of applications. So let's say in this low area. So e-bikes, e-kick scooter, e-monowheels, scooter, motorbikes, and e-quad. Here, there are some also useful notes for what concern the type of application for e-bikes and related world regions, let's say. But we're also taking about other relevant parameters. For example, the proportional method can be pedal assistant or throttle assistant, so which means power on demand. Kind of application. You can have a city urban for commuting. You can have trekking or let's say professional sports in mountain, e-bikes, e-street races, or even cargo for cities. Kind of battery types. So we saw before, in China, mainly are from lead-acid batteries, while in Europe, we are more concentrated on lithium-ion batteries, and the power range, let's say up to 250 volt or above 250 watt. Now, light vehicle definition and so on. So in this section, we will take more about the definition, and we will go in details in the electromechanical subsystem belonging to light e-mobility. For example, if we're talking about US, how to classify them? So there are 3 classes. So has been defined 3 classes from since 2014. This is most likely the same. Most of 30 states have standard regulation for it. So we talk from class 1 to class 3. So class 1 are the e-bikes that are only pedal assisted, so with no throttle, and there's a maximum assisted speed up to 20 miles per hour. Class 2, it's e-bikes with also have a maximum speed of 20 miles per hour, but can be throttle assisted. And class 3, which, contrary to the previous classes, are provided a support until the rider is up to 28 miles per hour, so not only 20. However, so a ride can activate the e-bike's motor assistant by pedaling. And also it's important that all classes in US limit the motor's power supply up to 1 horsepower or 750. For US, it's a little bit more complex. Sorry. We have an overall Europe classification, but each country applies a different rules by class, for example. So we have 4 classes as a European level. So class L1A, which are e-bikes from 200 watt up to 1 kilowatt, and the maximum speed is up to 25 kilometers per hour. So e-bikes L1B are bikes up to 4 kilowatt as a power, but has an assist speed up to 45 kilometers per hour. So this means also some cargo bikes or more professional bikes. Then we have L2E, so which have similar to L1B, sorry, but can be up to 3 wheels. So we will call the 3 wheels moped. And L6E are the bikes up to 4 wheels or quad moped. Of course, we discussed that every country in Europe also has a special rules on top of this guideline. For example, in Germany, we can see that the maximum power of e-bikes is up to 500 watt, and the maximum speed without helmet is only up to 20 kilometers per hour. So we also need to take into consideration each individual rules for each European country. Now, let's start with some legal definition and application norms. Let's say e-bikes are classified according to the power that electric motors can deliver and the control system, when and how the power from the motor is applied, so throttle or pedal assistant. Also, the classification of e-bikes is complicated. So, especially in Europe, since most of the definition is due to legal reason of what it's e-bikes, 2 vehicles will, and one constitute a moped or a motorcycles. E-bikes classifications also can vary greatly across country and local jurisdictions. There's also the general classification by control. So let's say motor assist by pedal assistance system. So what is generally called pedelec, and power on demand with a throttle. So what's called really e-bikes. So let's now go into electromechanical subsystem breakout. Here we can see what is called e-bike or a pedelec, let's say in this case. So we have different subsystems. So we have the power trains, so it can be in the middle, but can also in some cases be in the front wheel, on the front hub, so course, or in the rear hubs. We can have the human machine interfaces, so which one is communicated, the power of torque you can apply, so how is this the remaining charging of your batteries, the speed, all the information you have to interact with. The communication between different subsystems into the bike. The battery pack, so is important. So the battery pack has to be charged, and also to transfer and communicate the proper way the energy stored into it. Sensing, torque sensing, environment sensing, current sensing, communication, could be also connectivity with via Bluetooth or whatever it else. Charging, I mean, it's important to be standalone or onboard charging. Also here depends on the kind of application or kind of e-bikes we are talking about. And all the kind of accessories surrounded into the system. Now, The size of electronics, so the main parameters for what regarding e-bikes. So here we're talking about pedelec for regarding power traction. So the size of the electronics needed depends of many mechanical parameters. So as you can see here, the structure of the block diagrams, let's say, remain similar as the one in the previous slides. But the design challenges as such application is proportional to the power and the performance, like the maximum speed and the torque. So for example, we see that the torque can be between 30 Newton per meters up to 120. So the weight of the motor, so can be from 2 to 4 kilograms. The load capacity, so with only one rider, or 200 and more kilograms if you need to want to load some goods or whatever. Also, the weight of the chassis is one of the key points to take in consideration. The maximum speed, so we can go from 25 kilometers per hour up to more than 100 kilometers per hour. Depends of the kind of the application, the kind of specific e-bikes we're talking about, or if it's professional or for competition. And the rotational speed in rotation per minutes of the engine, so between 8 and 120 RPM per meter. Okay. Now, translating those mechanical parameters in electrical values, we can give here in the table. So electrical motor can be from, let's say, from 300, we discuss, up to more than 4 kilowatt. For e-bikes and pedelec, the level of power involved really varies quite widely. Of course, as the power increases, the battery voltage and the battery capacity increase obviously. So most of the time, the battery voltage have to stay in the range of maximum 60 volt. So this is the maximum corresponding value given by all the electrical safety standard made to protect the human being, but can be even higher if it's needed some specific application. And here you can see the typical uses, like for private use, you can have renting, tourism, city deliveries, and so on. Depending on the electrical vehicle power, battery chargers and motor drivers have various name and shape. For example, for light e-mobility, the charger is most of the time as a standalone power supply with an interface to adapt the output power voltage to the battery state of charge. The drive is mainly made with medium voltage MOSFET. So, for example, you can see also depends on the power. You can be, for example, below 50 watts. So in this case, you don't need any PFC. Active clamp flyback is more than enough. Medium power, you need a boost plus LC. For high power, we strongly suggest to use the totem pole PFC for have a better high performance, high battery, high efficiency, and high density plus an LC. When the power increase, so like for e-motorbike, e-cars, e-forklift, trucks, e-bus, and so on, an onboard charger is installed. So also because here in the previous case, the weight of the overall structure is a key point. So here, of course, the power is increasing. So we need to implement an onboard charger as installed in vehicle and can also use to fast DC wall box charger. In this case, for the driver, mainly IGBT or even SiC MOSFET are the preferred choice. Here we have major block diagrams, let's say three-phase block diagrams, let's say targeting the 12 volt and the 48 volt DC rails control. We have the major blocks involved here in the powertrain. So from the input side, we have the auxiliary or housekeeping power supplies. So that delivers the voltage for the processor here, which is the core and the brain of the system. So for the sensor as well, so with some LDOs and the MOSFET driver. The main reason for the processor is to generate, so he will generate the pulses needed to drive the motor. So the MOSFET driver or the dual MOSFET gate drivers will amplify those logic signals into a voltage, is a PWM voltage, compatible with the MOSFET gate requirements. So then we have the MOSFET that can deliver the power to the motor windings. current sensing amplifiers and monitoring the low side MOSFET to detect any failures or have a precise control of the loop. And here you can see several part numbers example, which are giving as a feedback and reference for each of those blocks. If we're talking about powertrain now, so only the power. So if you're talking about a 12-volt side, here we can talk about ACQ100, so that means automotive qualified or not automotive qualified, depends, because in some way some customers need to be automotive qualified or not. So it is really to the OEM's choice. So we have two ways of addressing it. One is with discrete solution. So this is especially for compact e-bikes powered with discrete MOSFET. So in this case, there are several opportunities. So we can go with a wide range portfolio from, let's say, 0.42 milliohms up to 25 milliohms. So here we're talking about a 12-volt power side. So we are talking about 40-volt MOSFET range. So we can go from the small 2x2 millimeters power MOSFET up to the most performance with 10x12. So TO leads, flat leads, or for really specific and high performance application, also in top cool side. So this means that we have the power dissipators can be on the top of the MOSFET in order to have a better power dissipation and have a better efficiency. On the other side, when we start to have more power, we can use integrated modules, so what's called APM. So for very compact solution for high power e-bikes. So in the for example, here we can see the typical block diagram for the modules. Here we're talking about 6x 40-volt rated MOSFET, 1.2 milliohms, embedded in a housing in a small package, which is 44 by 29 by 5 millimeter modules. If you're talking about 48 volt, here we have more or less the same approach, but of course, here we are targeting power rating MOSFET up to 80 volt. So of course, also the RDSM MOSFET has to be a little bit different. So here for discrete solution, we are targeting, let's say, around 1 milliohms up to 50 milliohms. Same kind of packaging, of course. And as well, we have more solution for integrated and modules. We are going from 12 to 25 kilowatt with 3 times APM 17 solution. Let's say up to 1 kilowatt with APM 19, or even higher with 5 times APM 12 solution. And also we take in consideration also the battery management systems.
Alessandro, just a quick question for me. Looking at these, I'm just thinking, from the designer's point of view, what have you got in terms of, or is there kind of reference design material that exists around these parts as well that will help?
Yes, this is a good question. Yes, on our website, there's a dedicated for this kind of application. You can find on the links, we can share links afterwards. Sure. You can find all the reference design, or with this presentation is to take into account with part numbers, some reference with some existing product and so on. Yeah. You can find everything on our website.
Sounds good. We'll share some links for that then with the follow-up.
Sure. So now, how to find the best fit for my drive? So we're talking about how to select the proper way. So here we have, we talk about in a different way. So here we take, for example, a 36 volt half horsepower motor. So how to address and which are the correct power gate driver and power switcher to address. So here we want to like to select, help you to select the appropriate power devices. So we have try to develop the simple approach to give you what we call a first order approximation. So the idea here is to give a closer choice for your application. And as we discussed, and this you can find on our website, to a complete portfolio instead of complete portfolio. So to drive you in the proper and the best way to select the MOSFET. And in the end, so depending on particular requirements, may be a little bit different. You select a MOSFET on a driver with parameters very close to the one given by the first approximation. So we have listed on the bottom of the slide the common parameters we have taken into account for making this first approximation, like VDDS, VRDS on, QJ, current phases, kind of packaging, cost, thermal, and so on. And here, for example, we can give some suggesting. So here we're talking about low voltage, let's say up to 36 volt rail. So for the first, here you can see the kind of MOSFET and FET examples and some gate driver example here on the right side. So here for the first approximation, we have used a trapezoidal modulation up to 15 kilohertz. So we limited the junction to 25 degrees Celsius above the ambient with a maximum of 85 degrees. So, and then we use an oversized coefficient of 2 times on the MOSFET rating and 3 times on the current. So the driver will match the MOSFET QJ need to turn on off and in only 50 nanoseconds. So here we have the table. So we can go, we take in consideration 36 volt and with a power range of the motor between 100 watt and 1 kilowatt. So of course, we need different currents between 3 and 45 amps, the kind of energy you need it, the charger you need, and the gate driver example we suggested for this application. Here we have the same table for the 48 volt batteries. So it covers the same power range for the motor and the application. So for 100 up to 100 watt up to 1 kilowatt. And also we have used the same assumption. And here you can see the MOSFET we suggested and the gate driver example. So in this case, of course, instead of 60 volt MOSFET, we need to use up to 100 volt MOSFET because 48 volt is a DC rails, but then you have to take in consideration all the spikes and into the system. As we've seen, a fundamental part of the powertrain dimensioning concern the gate driver selection. Several possibilities were shown in the previous slide based on devices already available as standalone driver. Another possibility will be to use our new NCD 83591, so which is a smart three-phase 60 volt gate drivers, which is designed for e-bikes and also for power tools. Its device has been released beginning of this year. This smart gate drivers has numerous advantage in the application. Its nominal maximum operating voltage it's 60 volt, but we can stand peaks up to 70 volt, and is therefore very suitable for powertrains with the battery technologies already present. In this slide, you can see the kind of application diagrams. So it means that with a companion microcontroller, with a companion microcontrollers and really few external components and the power MOSFET, of course, and the output powertrain is complete. So the device NCS 83591 can flexibly set the gate driver current to adapt the selected power MOSFET. This is also important. And the application EMC via a gate driver current strength with external current resistor you can see here. This device can work, let's say, with up to 30 kilohertz motor PWM, compatible with 5 and 3.3 volts. He also has embedded charge pump function, so it means that can operate up to 100% for duty cycle operation. And is ideal for light e-mobility, but also for many other applications for industrial consumer environments, of course, as well, including many power tools, or let's say actuators, cobot, and automated guided vehicles, for example. The NCD 83591 features several advantages, so we can very quickly summarize in this slide. So the FET gate driver is a three-phase BLDC with high and low side driver. You can adjust and program with a custom current, so not custom voltage, but a custom current from 5 to 250 milliamps through a simple resistor pin, and internally generated the 14 volt low side gate driver supplies. It's designed for robust design, so 60 volt operation with maximum up to 70 volt. He's also able to withstand up to 4 kilovolt HBM and 1 kilowatt ESD-CDM protection. And the high-side gate and source pin are tolerant with minus 10 volt down to minus 15 volt as a transient. And of course, design optimization is a 100 megahertz bandwidth. with configurable amplifier, charge pump for static DC as a gate driver, and again, it's very flexible, up to 30 kilohertz motor PWM with individual 6 gate driver controllers. Sorry, HMI and communication. An additional important subsystem for mobility is the human-machine interface and communication. So here we can see a little bit some block diagrams. So let's go in practice with these block diagrams. So you can see blocks that can serve are identified mainly. So for each block, you can see an example of optical applicable part numbers. So, and again, in the center of the system, we have a battery. So this is usually a one cell, let's say, which means one battery, lithium-ion battery cell in series. And here you can see, for example, we need full gauge to protecting. So the several interfaces, the CAN transceiver for communication or Ethernet, the point of loads. So for all the power management, the kind of protections, the chargers, and the load switches. And also the communication can be Bluetooth Low Energy with RSL 15 and 10, or some NFC and RFID controllers. And then, of course, as a charging, you also it becomes more and more common USB Type-C devices. 10BASE-T1S. So why it's so important? It becomes more and more common. We see more and common in industrial and becomes more and more common into automotive. Especially in automotive, we have this trend to move from, let's say, from a service-oriented to, let's say, a center domain to a zonal architecture control. So this means that more and more the location in terms of control units, so smaller brains and smaller engine around the systems. The advantage here to replacing, for example, existing solution like CAN, CAN-FD, FlexRay, and so on. So why? Because 100 megabits already present in the system or higher are too fast, while CAN-FD solution are not fast enough. So 10BASE-T1S is up to 10 megabits. So it's really provided the full bandwidth you need for those kind of application. Flexibility. So FlexRay, CAN are sometimes too complex and not flexible enough to adapt to the system. And this approach is also able to approach with a new architecture, like a zonal architecture system. So brings IP for services-oriented and software-driven solution. And as well, this is an Ethernet standard already available on the system. So as a solution we can provide, so depends if you want to have automotive or not automotive solution, because also we discussed before can be needed or not. So we have the NCV 7311, so which is automotive grade device. So this is a fully compliant Ethernet and BASE-T1S. So the standard is the IEEE 802.3CG, which was released in 2019. He supports half duplex, point-to-point, and multi-drops with physical co-layer avoidances. Is completely full compliant to the standards, and this device is integrated a MEC interface and a physical layer interfaces together in one point. So this means that you are able used to use a very simple microcontrollers with no needs for integrated MEC layer. And this is especially dedicated for full automotive device application. As well, we have the industrial grade, which is a similar devices, but is taken for industrial, so the NCM 26010. Which is a multi-drop Ethernet, as before, fully compliant to the systems, 10 megabit as a half duplex, SPI interfaces. We also have additional feature extra from the standard, like enhanced noise immunity, so which allow you to have a better communication or able to use the full speed of the bandwidth, whatever, in all condition. And again, so can be used for replace various wire protocols, HART, field bus CAN, RS485, and so on. So what we are talking about wireless, so we're talking, for example, about Bluetooth Low Energy, so can be used in industrial automotive. So one of the key points here is to address the lowest possible consumption. So in most of applications, you have coin cells, lithium-ion coin cells that you don't want to, let's say, replace frequently. So with RSL 10 and 50 solution, we are a leader on the market in terms of consumption. So for those kind of application, we are able to address up to lifetime, up to 10 years with a single coil. can be used for different applications where really the main power, the main point to take in consideration are the low power consumption available. Can be, for example, also automotive grade is a Bluetooth Low Energy 5.x ready. Of course, for this, everything is needed for automotive. We can provide PPAP, ACQ100 qualification, completely reliable assembly, so wettable flanks, QFN, high temperature ranges. We can provide, like we did invest in lowest power on the market, and also, which is very important for a design, easy to design with comprehensive software and hardware development kit, is a free FOTA, mesh, mobile test application, all the bundle solution on motor application, as well in industrial. And also it's ready to show various applications like multi-sensor, tracking tag, lighting, and smart car assets. Now, the core, let's say, e-bike's main battery is monitor and managing. So the core of the energy storage in e-bike is the main battery. So let's see which are the main requirements in the next slide. Let's say some of news on e-bikes. Let's say in China and Asia, most of e-bikes run on lead acid batteries, we see, because are cheaper and easy to control. Recycling of this battery is easy as well and almost full, let's say. An alternative is nickel metal hybrid, so an IMH, that has a good capacity, and can be disposed easily. However, it's quite costly. In Europe, however, the most common technology is the lithium-ion or lithium polymer. So their lifetime is longer and are very, very efficient. However, they require electronics to run and protect because the charge has to be done in a very precise way. Let's say typical battery capacity range can be from 300 watt-per-hour up to 1.2 kilowatt-per-hour. Weight, I mean, we're talking about vehicles, is also one of the key parameters, can be from 2.5 up to 3.5 kilograms, depends, of course, on the capacity. Pedelec, let's say with a 504 watt-per-hour battery capacity, let's say can have a range between 60 and 150 kilometers. So this is also to take into account more or less what can be.
Alessandro, I have a question here as well. When you think about the battery technology, and when I was reviewing the slides, I was really surprised to see that lead acid is still considered as a traction battery, I guess, for an e-bike, given its energy density, size and weight for the sort of equivalent energy. I really thought lithium-ion would be pervasive everywhere. Is there a choice to make here, or is it simply that it comes down to cost and ease of control and the price point of the end product?
Let's say this is exactly what your point. So the only reason today to use, let's say, lead acid batteries in this kind of application is cost, easy to drive. So this means very cheap solution to address. So this is why it's well used in Asia, where we are talking about very low cost and cheap application. Right. So in Europe and US, we are delivering more complicated and more high performance e-bikes or pedelec. Yeah. So while in China there's a huge market, and we also need to consider also how wide is the market in this way of very, very cheap and simple e-bikes as an alternative of all kinds of transportation. Yeah. So the cost have to be more or less in the range of a standard bike.
Yeah. Okay.
Sorry. And the last point, let's say, typically, also for safety reason, for e-bikes or pedelec, we are talking about 10 cells in series. So let's say around 36 volt as average battery voltage. So let's say up to 504 watt-per-hour. So this is where this number came. So here also we say agenda block diagrams for the solution as presented previously. So most of the units in the market are around 36 and 40 volt, typically, let's say. And of course, we can have some additional range up to, for example, 52 volts or a little bit higher. But this is really the main area is between 36 and 40 volts. Here we have some different parts, let's say main battery here, external power supplies. So of course you need the protection. So you have also the charging the systems, so the protection, the self monitoring and balancing. You need a constant voltage current regulator, current transceiver, or time-based T1S, as we saw before, which is one of the main trends now. And of course, the interfaces can be the GPS, GSM, Bluetooth Low Energy, NFC. And as well, we see more and more common or more trend to use also for charging this kind of application, USB Type-C, especially with the new trends to be able to manage handling power up to 100 watt or even higher will be. On-board, off-board charging solution. So this is also important. So we mentioned before. So here, one of the main points is to have very high performance in terms of efficiency and ultra high density, because this is something you need to have exactly on board. So take space, take size, and weight. And every single grams you add, it's a small piece of battery less, let's say, millage you can address with one charge. What we are suggesting as for power, let's say above hundreds of watt, is PFC, totem pole PFC. So for who is not familiar, totem pole PFC is a bridgeless PFC. So basically you're going to remove the input rectifier bridge. So is of course a solution which is more, let's say, high performance, but is ready to achieve a much better efficiency than the standard system. So we as onsemi, we are the only one on the market with an analog solution, so not MCU based. We are the industry first mixed signal control, so it's based on a state machine core dedicated to totem pole PFC. So this means that it's easier to implement compared to existing totem pole solution. It's very cost effective, fast to go to market, because basically you don't need an expensive software update. If you are an analog designer, power design is like designing a standard PFC, and you don't have to deal with microcontrollers or more software. And this is a device which is able to handle up to, let's say, from few hundred watt up to 3-4 kilowatt solution. As a secondary stage, so we can say, okay, sorry. So which are the advantages? So we say that existing solution in the market as MCU based, high BOM cost, because you need more solution, you need a microcontroller, you need all the components around, you need to software code development, so time for this, more resources, and a complex design which is time consuming. So for what regarding onsemi, we have the family on 60, 80, and 81. So 60, 80 is for CRM control, so low power. 81 are for CCM, so high power, let's say high wattages. Is very cost effective compared to a totem pole based on MCU. Optimal BOM, bill of material, so you need only what is needed as an analog design, and very fast in development, because it's a really tailoring an analog design. On the other side, so we have the DC part. So from the PFC, you have to extrapolate a DC line. So here we're using very high performance LSC controller. It's a current model. We have NCP 3994. So this is a very high integrated half bridge resonant converter. Here we have a high input voltage up to 700 volts, and with a switching frequency from 20 kilohertz up to 750 kilohertz. So allowing to use from a standard MOSFET really up to, for example, wide bandgap solution, even like, for example, ready for GaN solution, to a very, very compact and high performance application. As well, you need some drivers. So what we can suggest here for the better performance is the NCP 51561, which is a 5 kilovolt isolated high-speed dual driver. So here is important dedicated for MOSFET and SiC. So here is important to have a very high performance matching, very small delay time, so only 36 nanosecond propagation delay times, and only 8 nanosecond delay times matching between the two channels. It's important here to have a very high dV on DT immunity. So the device is able to manage in more than 150 volts per nanosecond, because in this case, you already have to have high switching, hard switching application. So having a very high immunity is important. And of course, it comes with different anti-voltage lockout for addressing to matching the perfect solution for FET or silicon carbide. So as a summary, so since we are running out of time, so very close to it, what we can say, e-vehicles, like e-vehicle solution, we saw at the beginning is a very growing, is already a big market, but it's still growing and is really growing fast. It's difficult to cluster, and today there are not really standardized solution at this time. We expect to have some consolidation in the future. We have, considering the performance and how wide is the market, we have a widespread technical solution needed due to the big range in power and voltage. So it can be from 12 to 200, high power from 200 watt up to 4 kilowatt. Each incoming request need to be looked in simulation and a sweet spot between performance and cost. Considering the application condition in simulation will enable you, so with support from onsemi, to find the sweet spot concept for your project. So please get in contact with us or our representative. And also what we are providing as onsemi is a STEMI simulation model for our power and driver parts, especially with the new MOSFET technology, which are able to get the perfect solution for your project. So that was everything from my side. I think we stay perfectly on time. So let's see if we have any questions.
Indeed, thank you very much, Alessandro. Your timing is impeccable, and thanks for the interesting insights. It's really you can see it looks like the industry or this sector is yet to mature and probably driven by some legislation and so on as well. But I think as a manufacturer there, you've coped with the whole kind of spread that you see in the power requirements for these type of vehicles. So we have a few questions, and a few of the slides put me in mind of questions as well. Let me just dig out where the Q&A's gone. So one of the things that you touched on, and I think is almost, looks like perhaps people weren't expecting this, that is the level of Ethernet technology that we're seeing come into this sector then. So for you then, what's the advantage to move to 10-base T1S Ethernet technology then?
So this is a technology which is start to be more and more, let's say, requires in industrial and automotive. So we also have the with coming also, and have to come more so for e-mobility. Let's say why? So the main advantage, and this is a really good question, is that the main advantage to move into a single multi-drop Ethernet technologies is that you're allowing only one wire, okay, which can replace all the several different cables. So this means that you are able to reducing the number of cables, so and also the cost and the weight, because especially for something which is moving, it's really important, especially with a battery. And also, this is important that you are really able to improve assembly and diagnostic through output.
Yeah.
So those are the main characteristics and the main advantages to move into a technology compared to existing communication standard.
Yeah, and we're seeing this in other applications as well, I think, but related. If you looked at, for example, urban air mobility, and you look at some of the developments there, so we're looking at vehicles at some point, aren't we, that will, fly us from the airport to our final destination kind of thing. And it's the same kind of emphasis on how can we reduce weight and simplify and so on. Exactly. You mentioned two parts as well, I think, or you mentioned that it can be both automotive and industrial grade parts. Exactly. And what, to me, I think it is based on application, of course, but are there any other considerations why the customer would choose industrial over automotive or vice versa? Or is it simply reliability and temperature range?
It's simply reliability and temperature range. Of course, there's also the kind of packaging and testing. I would say from a design perspective, the devices are very similar. The function are similar, but of course the automotive grade it's designed for to be used in hard automotive environment. So it means we have a high temperature range, all the design FMA, so all the processors, all the PPAPs needed for a standard automotive environment.
Okay, thanks. Also, a question on, I guess, more general point around power supply, because at the higher end, we're looking at high performance power supplies, really, aren't we? And why is it important? One of the questions is, why is it important in those power supplies to use isolated gate drivers?
Yes, so that's also another good question. So why is it important? So we saw before that we are moving in direction to have more compact solution, high density, high power. So this means sometimes even high frequency switching solution. So when you have high frequency switching and also you have a higher load current, and we'll talk about hard inductive switching, it results in a very high dV on dt. So this dV on dt can introduce heavy disturbance current into the other circuits, and isolated gate drivers helps really to reach a high dV on dt, immunity, required with a hard switching power supplies. So it's really a matter of having a perfect condition. We can discuss even later if someone is interested. So we have different materials on how this fast dV on dt are really affecting, for example, the turn on of a low side gate driver, even if it has to be off. So those are all the effects that to be taken into consideration.
Right. Okay, and then as you said, I think if somebody wants to dig into this a little bit deeper, they can certainly find you, I guess, on LinkedIn, but we'll share contact details on the Q&A doc that we follow up with. And also another question around the CCM bridgeless totem pole. What's the maximum switching frequency achievable?
So in a CCM, so in critical induction mode, let's say compared to the standard solution, can be much higher. So with let's say the maximum achievable switching frequency, if we're talking about, for example, using wide bandgap switches, so SiC or GaN, let's say we can be reasonable even up to 150 kilowatts. Okay, but in theory, it can be much higher. So it can also go almost double. Okay, while in a standard PFC, we are in the range of few tens of kilowatts. Yeah.
Okay, again, I think if there's something deeper behind the question, people can kind of reach out to us. We are going to run out of time, but I had one more question, because I was thinking about you were talking briefly about the Bluetooth connectivity and wireless connectivity generally, and coin cells and so on, and long battery life. And of course, this all relates to doing as little as possible for as long as possible, I guess, in order to get long battery life. But another topic comes into that, which is around battery characterization. And I wondered if it might not be your area, of course, but whether you knew if onsemi were doing any kind of characterization around batteries for the products that you're bringing to market.
Yes, of course, all the product, when we are mentioning the kind of power consumption and the consumption we have, of course, are done with real battery characterization. So we are using sometimes the most common battery present on the market. And I think even if this one can be used or can be found somewhere on our website. So for example, for Bluetooth Low Energy, we have our community forum in which everyone can ask information, can ask questions, and our experts are able to provide those kind of information, or even other users. We're already phasing out this topic.
Yeah, that sounds like a useful resource. We'll certainly add the link for that when we follow up with the Q&A document. Is there time for one more?
Yeah,
just with a couple of minutes, just which charging speeds are standard and where is it going in the future for light EVs?
well, this is a good question as well. I don't think there is a standard yet.
No, me neither.
I think it's really depend on the kind of which is the final application for light vehicles. So can be, for example, that it's you need to charge your devices or your EV overnight. For example, some forklift you're charging overnight and they're using all day. Could be, for example, some let's say opportunistic charge. So then you're moving from one point to the other when you're charging. And in this case, it has to be maybe faster, maybe 2 or 3 times charging, free C, so 3 times the charging current, or let's say you have OBC in which you need to charge or charging the battery. So there's no standard yet, and I'm not sure will be a general standard for all, because even light vehicles, it's quite wide.
It's a very diverse world, isn't it? So that's what I'm thinking. Just looking at the question was, I'm not sure that sounds feasible when you've got kind of plug-in chargers at one end for a very small e-bike through to, like you say, industrial LEVs.
Exactly. Well, let's say for small e-bikes, for example, you're charging like a 350 watt, probably a good charging times with an external suppliers could be probably 2C, so twice the current. It's feasible, reasonable. For others, it really depends on the application. You can have a fast charger or a standard charger, and this is one of the main topic to take into account where you are designing lighting vehicles application.
Indeed. Right, we have run out of time. 1 minute to go. So I just want to say thank you, Alessandro, for today's presentation. Lots of great information in there. And we will follow up with everybody from the Q&A perspective. They'll be answered in writing and be made available to all participants. Should anyone wish to watch the webinar again or share it with others, it will also be made available on demand soon. And finally, there is a short survey coming up, and we'd be grateful if anybody watching would provide some feedback and help us improve future webinars. And with that, I'll say thanks again, Alessandro, and goodbye, everybody, and have a great rest of the afternoon. Thanks.
Thank you.
Bye.